Hey, welcome back to Math with Patrick. Today's October 12th. We are joined by Quill, and together we are solving problem 285 from the Daily Epsilon calendar. And the answer today should be 12. So this blue region represented by the variable x should have an area of 12 today. And it looks like we are constrained in a square. Like I'm assuming that these are all going to be 90-degree angles. And then noticing that all of these sides are congruent to each other. This last side, again, assuming that we do have a square, assuming that we do have 90-degree angles, that forces this whole side to be congruent to all the other ones. So we have a 6 by 6 square. And then it looks like we have essentially just the long diagonal here. And then we have another kind of diagonal, and it seems to bisect this bottom side. That's what these markings mean. It just means that this length and this length are equal, or that bottom side is cut in half. And we just want to show that this region has an area of 12. Well, starting with this 6 that we're given, I think it's pretty clear that the area of the whole square is 36 square units. And so I think we can try decomposing some other parts of the square and learn about their areas too. Like this bottom left triangle is just going to be exactly half of this square. So its area is going to be 18. We also have this triangle on the right side. I'm kind of noticing that it's essentially half of our whole square, or essentially 1/4. So this triangle kind of on the right side of the square should have an area of 9. And I don't really know the area of this one. It's like normally when you try to find areas of triangles, you just do base times height divided by 2. So for here, base would be 3, that's half of 6. And then times height would give us 18. Dividing that by 2 does give us this 9. But the triangle where we have the x and this triangle over here are a little bit hard to just calculate directly, because this height is unknown to me right now. I'm not really sure how far into the into the square this goes. One thing though, we do have vertical angles here. Vertical angles are just angles that are across from each other when lines intersect, and those are congruent to each other. Also, using the assumption that we have a square again, opposite sides in squares are parallel. And so I do have a parallel lines and transversal kind of situation. So these alternate interior angles are also congruent to each other. And therefore, we do have similar triangles in the diagram. And if we have similar triangles, then I know that their lengths are proportional. So this is a 6 and this is a 3. So essentially every linear distance is halved going from the big triangle to the small one. So what's kind of cool is I don't really know what this height is, but I do know that this height is also halved, again, because they are similar triangles. Any linear distance is going to have that same scale factor, which we can just find is a times 2 or a divide by 2, depending on which direction you're going. So this actually lets me solve for h. I'm going to kind of can this idea for a sec. I do want to come back to it, but I just found a different solution. H plus h over 2 should give us that whole 6, because that's, again, that vertical side of the square. So 3 halves h is equal to 6. We can multiply both sides by 2. We can divide both sides by 3. H is now equal to 4. And then it's a fairly easy problem now. We could just do 1/2 times base, which is 6, times height, which is 4. And then I'm doing this part first. This 1/2 times 6 is a 3. 3 times 4 is 12. So that's one way to get your answer. And maybe the other way that I was kind of getting at with these shapes, it also kind of relies on the idea that these are similar triangles. I know that this area of the small triangle is going to be 1/4 the area of this top triangle here. The reason being is that if we did some kind of area formula, and we did, area is 1/2 base times height. Again, the base is halved because they are similar triangles, and the height would also be halved. And so overall, we are getting a scale factor of 1/4 to go between the areas of these two triangles. From there, I can do a little bit of kind of composing shapes together to create an equation out of the areas. So like the whole entire square is 36. And this should be equal to, when I add this triangle, which I'll do an 18, to my x triangle right here. So I did this big triangle, this triangle right here. And I don't have an expression for this triangle on the right side just yet, but I do know that it's just this 9 and then take away my x over 4. So never mind, I do. I can add the 9 and then take away the x over 4. So I'm just talking about this right side. And then now I have another equation where I can just directly solve for x. I don't need to worry about that intermediate height variable. Here it looks like we get 27 plus 3/4 x equals 36. This means 9 is equal to 3/4 x. And then we can multiply both sides by 4, divide both sides by 3, and then now we can directly solve for x, and we also get 12 this way. Either way, I think my solving still relies on the fact that I was able to prove that these two triangles were similar. But once I knew that, then I could learn more about either the heights or the altitudes of both of these triangles, or I could just do a little bit of comparison about the or with the areas directly. So either way, area is 12, and we're all done. So thanks for watching, and I'll see you tomorrow. Bye.